Okay, thank you very much to the girl who's recording first. Okay, anyway, the idea in this problem was to, well, I must remark that when you're qualitative, you have to design your own variables, and there is no unique criteria, no? I am wondering, you guys from education, do you see some mathematics? What? Do you see some mathematics in education, uh, or you focus in different directions? Let's say when you are in education, you focus qualitative or quantitative depending on the. Welcome back, Red Pill. Later, I arrange the attendance. So the issue is that there is no unique criteria, and it's an exercise of creativity. In this case, when you analyze demands, price-demand relations, the variables are already there. Are you comfortable there? Really? Maybe you can over there. I don't know. But normally Eve is there, but she's not here today. Probably, I don't know. Anyway, it's her first absent today. And I think the other absent, there is another absent. Kingsley is here. Okay. No, by chance. The together, no, absent. Okay. The issue is when you analyze you have a plane. You have a plane. That's plane. Let's assume, well, this plane can fall like this. Hong Kong Express, let's say, which is the most popular for going to Japan. I think if you go to Japan or from Macau, you can depart also. I don't know if Air Macau goes there. I never tried. But normally, the airlines play with the price, no, for controlling the demand. Of course, in hot seasons, they increase the price. Who can tell me why the airlines increase the price in hot season? Because there are more people who want to travel, right? And then when they increase the price, what they are doing? Reducing that amount of people who wants to travel. They try to reduce it, no? Because if they increase infinitely the price, nobody will go, right? So there must be a limit, no, of that price. Now, of course, you will expect a relation like this. You will expect price, demand. Let's call it X. This is demand. Demand is amount of people, right? And this is price in Hong Kong dollars. Let's put Hong Kong dollars. You will expect something like this, more or less. Right? When the price increases, the demand decreases. This is how the airlines control more or less the issue. Then, of course, we have to design the experiments here, right? Well, there is a third variable here, is the time, no? Time. February, March, April. 16, 12, blah, 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 all these things. And those are prices. That table on the board displays some prices. Let me show here. That table displays the prices. And we want to design some experiments. Of course, the experiments are already there because you can see the website every day. But let's go here for a while. You have the variables. You have different options here. You can apply statistics and study the possible correlation between variables. But the problem with that is that statistics doesn't tell you how those variables are connected exactly. The statistics will not tell you that. Then dimensional analysis will tell you how. Therefore, at least for this example, I will only use dimensional analysis. Later, of course, I will send you by email, most likely tonight, if not tomorrow very early, a more complete example. But then you have three variables. You have price, demand, and time. Time, no? Time is every day. There are hot days, hot seasons, days where the price climbs to the sky. Chinese New Year, for example, etc. So if we use dimensional analysis, we know the dimensions of the price are the currency, Hong Kong dollar, the dimensions of the demand. This is dimensionless because number of people is not a unit. But I will put it number of people. So this is dimensionless. And finally, the time, the units of time. In this case, are days. Days, right? Because you can see one day, done. So if we apply the Buckingham theorem, which you saw before, you have three variables. Two dimensions. Now, even if I don't apply the theorem, I should suspect some connections between certain relations. Then the first thing which comes to my mind is that I want to create, I will delete this. I want to create a relation, a function, price, demand, and time. Some dimensionless combination. What does it mean by dimensionless combination? There is no dimension. No dimension. There are no units. The combination, the final relation has no units because the units on the left are equal to the units on the right. These are only words. Let's go to the grain. I can say that I will call this better M. M is money. Money. And I will mark this as capital D, days. D is days. So we have the units. Money is price. Time to be constructed as price multiplied rate of change of price, for example. This is just an example. This is a possible combination, possible. But then I will be tempted to say, the relation at the end, by using these things, and even intuitive, you will realize, you will obtain that the price is equal time divided, multiplied by a rate. This is the simplest expression you can obtain here. Because we know when you execute the experiment, you have to execute two experiments. Experiment one, let's do the experiments here. Experiment one. You plot price, demand. Then you realize that when the price increases, the demand decreases. So there will be a moment, there will be a minimal demand here. Let's assume this is the maximum here. And let's assume it goes something, at the end we describe something like this. Or in the most simple scenario, let's do the simple scenario. Something like this. When the price increases, the demand tends to zero. And there is a maximum demand. What is this maximum demand? Equal to what? The capacity of the plane. The plane has a maximum amount of seats, no? Available. So for a single plane, there will be a maximum. Of course, this will not be perfect. This could be something like a curve or something. But this is your first experiment. Then you know, as a consequence, that the price and the demand will be inversely proportional. Of course, more complete, I should put some indexes, some power here, and then after with regression and so on, I know what is the power. But let's do it simple. Let's put it like that. This relation with time is more complicated. I plotted this in Excel, and I will show you what was it. It was this is the chart obtained. Let's share here. This was the chart, but of course, it's difficult to find a specific function. But something you can see here is that for sure, the relation is not linear. For sure, it's not linear. The price time, no? The vertical axis is the price of the ticket. The horizontal axis is the days, time. So when I see this, actually, where is the pointer of this? Here. 1 second. When I see this, I can start to conjecture things. But initially, I see some peak, comes back. This is obviously a hot season. This peak. Those are days where many people are willing to travel. So the airline increased the price. If I have a plane, I increase the price until I reduce the demand to the size of my plane. I don't know how to, if that explanation is right, is understandable for you, but the idea, I want to fill the plane. Let's assume this is the plane, this is classroom is the plane. I don't want the plane empty. If I increase too much the price, the plane will be empty. If I reduce too much the price, I will lose money because millions of persons outside wants to occupy your seat. Then I will increase the price by purpose such that the amount of people who wants to travel exactly match the amount of seats I have in my plane, right? This is more or less the idea. Then that's why the airlines do. Then increase the price here, also here. So it looks more or less like an oscillation, whatever. So at the end, of course, a deeper analysis, but this oscillation is like damped or so. At the end of the day, this expression could be correct only for this region, for this small region here, this linear. But for this region, no. And for these regions, no. This is more or less constant. This price here is constant. So there is no correlation in between 5 to almost 15. There is no relation between time and price because the time changes, the price doesn't change, right? So there is no correlation. So you will have the tendency to believe, no, there is no relation between price and time. Actually, there is, because in other days it will jump. It's what happened here. It's what happened here. This is a hot season, evidently here. Great. Well, anyway, this for some people could be some kind of oscillation. So there are many potential expressions. This is for the first part of the graphic, first part, where rate is the rate of change of price, rate of change of price. But if we consider this as an oscillation, approximate oscillation, more or less damped, then at the end, you will have an expression like this: price equal inverse of the demand multiplied by some constant, which will create the consistency of the units, cosine of the frequency, measuring the frequency like the distance between these two peaks. Time. And this frequency is measured such that omega period is 2 pi multiplied by an integral. So at the end, omega is 2 pi and c. So this is just playing with the math. Well, you don't have to worry so much. The important is that we find an expression for this. Price, oh, here. There is a compact expression between price, demand, and the time. And then at the end, this is the expression with which you can play calculus, you can start to apply maximum, minimum, whatever. Of course, this is not perfect because this is not a perfect oscillation. You can see this is shorter than this. And for considering those shorter things, I have to put something here. I have to put some term here, which create the effect of decreasing the price. And that term should be something inversely proportional. It could be concentrated here in R, because R could be maybe 1 over T to some power or whatever. It doesn't matter. So here the important is that you understand the sequence now. Now the details, of course, you have to go and study a little bit more, but the idea is I could find an expression between price, demand, and time. Executing 2 experiments. Experiment 1, price, demand, fixed time. Fixed time. This will give you something like this. The second experiment, price, time, fixed demand. Fixed demand, see, the demand doesn't change here. It's a fixed X. What does it mean fixed demand? I have a plane. I cannot change the number of seats in a plane, for example. So, well, this, of course, you have to think a little bit about that. But the point is, you can find a compact expression between price, time, and demand. After that, of course, you can start to play with calculus, etc. Now, if you want to analyze deeply, because the last class we saw matrices a little bit, then I will put an example where, well, I show you an example in that class about the eigenvector applications. Actually, was the photo. You remember there was a picture. There was this axis, and if you deform the picture here, like this, you make some distortion. This vector doesn't change. So this is an axis, an important axis, this direction. And this was an eigenvector. I think I showed it to you last time. But here, what I want to remark is that. Let's go to this figure now. Let me show you something. This ellipsoid here, this ellipsoid here is more or less a relation between price and demand, at least for the positive side. When the price increases, the demand goes to 0, right? If you ignore this side, the negative side, because the prices cannot be negative, if you tend to go only this part, the positive part, because positive demand, positive, the relation price demand is more or less like this, an ellipse, like this. This part, this is an ellipse. I can complete it like this. Price demand, more or less. Now, well, there is a chance that that ellipse is not perfect. There might be cases where that ellipse, because already I have the principal axis here, there is a chance that the relation is something like this. Then of course I can find the equation of this, the equation of this, which we give you like p squared with some coefficient plus px plus x squared equal 1. More or less, this is the equation of an ellipse. And then I want to find the axis of symmetry for this ellipse. So in other words, I want to find x prime, p prime. And these two guys are the eigenvectors of this. So are the axes of symmetry of the data. And this is what I explained the last time. And these axes are important because it's very important to know the orientation of your data. It's not only plotting. Sometimes your data has some patterns. You can have a data here, and maybe your data seems to be oriented in this direction, and I want just to rotate this axis such that this axis crosses exactly the center of my data here. And I need a perpendicular one as a reference. This guy and this guy are the eigenvectors, which we were finding the last time. So that's why the eigenvectors are so important, and they correspond to some eigenvalue. For a more concrete example, let me share here. Let me find first here. This one. No, this one. Share. Okay, wait. What I'm talking is that there is a chance that the relation price-demand is not as perfect as you imagine, and instead it follows this result like this. Of course, adjusting the numbers, no? The numbers are different. This is the demand, this is the price, but you have to change the numbers. It's the same. So anyway, this axis, this orientation doesn't tell me anything. I want to know the center of my data. I want to know which line crosses here and which line crosses here. And the center of my data is defined by the eigenvectors of this data. And no. That's why I say you have to cut this part, of course. This part you have to ignore. But of course, you have to complete we complete this is for you to understand what we are doing. But I already said before, and actually I already said that the price, this part you ignore, this part you ignore, and this part you ignore. It's only this part. That's why I painted this part only. No? Well, I have to complete it for you to understand what I'm talking about. Then at the end of the day, when you calculate eigenvectors and eigenvalues, for example, if you calculate the equation of this ellipse is this one. And the matrix corresponding to this ellipse is this. This phi is here. This 4. Minus 4 corresponds to 2 times 2. And this phi is here. If you diagonalize, finding the eigenvalues of this is the diagonalization of this matrix. These are very advanced techniques. I don't expect qualitative people to use it. Actually, I don't think you will need it unless you analyze pictures or pattern of pictures also. But the eigenvalues, for example, of this matrix are these 7 and 3. So it means, what does it mean 7 and 3? That in my new axis, in the rotated axis, my matrix is 7, 3, 0, 0. It's diagonal. It's a diagonal matrix. And the eigenvectors are these guys, 1, 1 minus 1, 1 in this matrix before. And let's see what is 1, 1. 1, 1 is this vector here. crossing here precisely is the vector 1, 1. And minus 1, 1 is the vector here perpendicular. So what I have found is this axis, eigenvector 1, eigenvector 2. So at the end of the day, what the eigenvectors are telling me is what is the orientation of my data, and I am finding the axis of symmetry of my data. And sometimes it's very important to know that, because this can give you an additional information which otherwise you cannot find. In this case, it's easy. If you find the equation, you can just create the matrix with the equation, with the variables, because you can put this entry is x squared, this is the mixed xy, yx, and this is y squared. I mean, this notation, you will understand it later if you go deeper in this section. But this is a case where eigenvalues and eigenvectors are applied. And the axis of symmetry, what are telling to me? That if I rotate this data around those axes, I will just obtain the same configuration. Nothing changes. Yeah. And in some cases, in some scenarios, this might be very, very important. Okay. So now, what kind of data? It depends. In this case, what's price demand? In other cases, could be different. And something else I want to remark is that let's assume you are analyzing price demand for a fixed plane. You have a plane here. The number of 6 is fixed, so it means you have to fix x, the demand you wish. And the time coordinate doesn't appear here. It's a third dimension, which doesn't appear. But you will see then fluctuations of the prices like this. Like this, like this, like this. Only when you analyze the price time in a different experiment is when you realize the behavior, which is what it was done here in this. Because actually I wrote this paper with these guys, but I realized that there are some improvements we have to do, because we had to include we didn't plot the third dimension. There are some details I discovered just now when I was revising But here, Excel doesn't give you an equation. I must remark that if you try to make an equation here, the tendency line, Excel will just give you this. The straight line is this. The tendency, it doesn't give you anything. It doesn't give you in reality the details. This is a peak here. You can approximate this to a bottom here and a second peak here. It looks like a damped oscillator, like a wave, no? And this is represented by this problem. So now, there is no general rule for finding expressions like this. Of course, I could do it like this. I am training in this. I understand you are not training that. But what I want you to understand here is that it's not enough for finding correlations between variables. Not even knowing that the correlation is positive, for example, or negative. The correlation, statistically, the correlation between price and demand here is positive or negative. It's negative, actually. Because when one variable increases, the other decreases. When you calculate statistically the correlation, you will obtain negative value. But statistics doesn't tell you what is the exact dependence of those two variables. This is obtained by you via regression, dimensional analysis. You have to do more things. Okay? Those techniques, of course, you will be developing yourself eventually, and so on. So this is the first part. I wanted to start with this example. I will send you the details later, but I will scan and send to you some example. But for the moment, we have to continue, and then I want to know if you have questions or so. Well, the exercise is simple. You have a plane, actually different planes. Hong Kong Express can have planes with different amount of seats. This can have 40, the other 100, the other 200, okay? So for each plane, when there are more than one plane, is more complex, the problem, of course. Because you want to fill all the planes. And then you fix the price such that you can fill the plane but still you don't lose money. Let's say ideally there are no more people outside waiting. Let's put it this way. Okay, I will repeat this part because it's very important. Plane. How many seats do we have in a plane? 100, 200? Hong Kong Express, how many seats? I forgot, it's in the paper, what? For the models they use, I think they use an Airbus, whatever. Let's put it 150 seats. And actually, I forgot to mention the class 1, class 2, because the prices changes, but that's another complexity I don't want to get involved. I am the owner of the airline. There is a hot season. Many people want to travel. Let's assume 3,000 persons want to travel. Will I keep the same price as cheap as usual? Then I will say, no, I will increase the price. And then when I increase the price, what will happen? This amount of people who want to travel decrease. They say, oh, no, it's too expensive, I cannot pay that. And ideally, the prices increase up to some point that I can at least fill my plane. So if this decreases until 150 guys who want to take the plane, for me, it's okay. That's the idea. But if I exaggerate, if I increase it too much, then maybe only one person wants to take the plane, and then I start to lose. I still lose. So it's a complex problem. It's a complicated problem. This is a complex problem, so I don't expect you to develop it fully, but it's one example where this kind of matrix theory, eigenvalues, eigenvectors, and whatever can be applied. Yeah. At least qualitatively speaking, you understand what I am talking about, right? Great. Now I will stop sharing this part.